Hi folks, welcome to section 2.7 where we're going to talk about linear inequalities now instead of equations. I want to say to start off with that much like we did with section 2.2, we're going to split this section up. This section also contains some information about absolute value, and we're going to separate that and we'll just do one section all about absolute value instead of splitting the absolute value information among several sections. So for right now, we're only concerned with the part of section 2.7 that talks about linear inequalities. Now, the reason we care about a linear inequality is that many times an equation might not exactly describe what's happening in real life. For example, you've budgeted $300 for food this month. You spent $150 of your budget at the grocery store. You know that on average, a meal that you don't cook for yourself, if you go out or pick up or something like that, you know on average that costs about $8 for your usual lifestyle. So how many meals can you go out to eat or pick up or whatever instead of cooking? Well, in this scenario, you could spend $300 on food, but there's nothing that says you have to spend excuse me. There's nothing that says you have to spend exactly $300 on food. You might spend less. So an inequality will help us describe situations like this and others. By the time we get to the end of this section, you should be able to convert between an inequality, interval notation, and a graph. You should be able to solve a linear inequality, and you should be able to solve a compound inequality. So in this video, we're going to start off by talking about interval notation, because that's one of the main ways that we'll be able to give an answer to an inequality. And then in the second video, we'll talk about solving inequalities, and in the third video, we'll talk about compound inequalities. So before we write this as interval notation, I want to introduce you to a term that's called set builder notation. This is when we write a set of numbers with either a description or some kind of definitive property. For example, if I wanted all the real numbers greater than 3, I would write that in set builder notation like this. And you read it as the set of x such that x is greater than 3. Now we'll often shortcut that because at the end of our inequality, we might just say x is greater than 3. And that's okay. But if you get asked for set builder notation, what they're looking for looks like this. We could graph that on a number line. If we want numbers that are greater than 3, that would be numbers like 4, 5, 6, so on and so forth. So it's the technology here is not great at making the arrow big enough to see, but there's an arrow on the end of that to indicate that it keeps going. Notice that I have an open circle at the end of my blue part here. We'll talk some more about that in just a moment. Well, we could write this as an interval starting at 3, and it goes forever to the right, so we say that's going towards infinity. So this is sort of a more compact way of doing it than having to draw this graph every time, because sometimes this is a little bit difficult to visualize in your mind. So this interval includes all of the numbers bigger than 3, but none of the numbers less than 3. Alright, so a couple of things to notice. The open circle that you see and the parentheses at the beginning of the interval both mean that we are not including 3 in our set. Alright, because 3 is not greater than 3. 3 is greater than or equal to 3, but 3 is definitely not greater than 3. So we can't include 3 in our answer. The arrow that I pointed out means that the set continues forever to the right. Well, so if we wanted all the numbers greater than 3, why didn't we just start at 4? Well, because there's all these decimals in between 3 and 4 that are greater than 3. 3.5, that's greater than 3, so it needs to be part of our visualization of this set. What about 3.1? Well, 3.1 is greater than 3. So the open circle and the parentheses indicate that we're including all the numbers up to 3, but not including 3. So there are several common types of sets that we're going to get into, and I want to just sort of run through this quickly. If I have x is greater than a number, that's like what we just saw. So the interval notation would be the number, whatever it is, to infinity. And if we were to draw a graph, I'll do my graph in a different color. This would look like an open circle and then going forever. The open circle's at A. All right. If I had less than A, then that means my interval goes the other way. And so if this is my number line, and I have a point A again, whoops, that's not the one I want. Then if I want the numbers that are less than A, those go to the left on the number line. And so the interval notation has a negative infinity to indicate that it goes forever to the left. If I add greater than or equal instead of greater than, then the parentheses changes to a bracket. The bracket tells us that we're including A, okay? And I'm running out of room in my little boxes. They're not quite big enough for me to draw, so I will put some graphs down here so that you can see all of them. If I wanted to do A to infinity, and this time I'm including A, then the way I show that differently on a graph is by putting a solid dot continuing to the right instead of my open circle that I had here a minute ago. On the other hand, if I wanted to do less than or equal to A, then that would look very similar to less than A. It's just that now I have a solid dot going to the left. So solid dots mean that we're including whatever the number is. Open circles mean that we are not. Now we may sometimes also see some interval examples that have two endpoints. They go from one number to another number. So if we saw something like A to B, then that would look like, here's my number line, it's got A and it's got B. And the set of numbers that we're talking about are all the numbers in between A and B, but not including A and B. If we were including them, we would have to have equal to's. And in fact, that's what the next one is. So this next one is when I have A less than or equal to X, which is less than or equal to B. So that's all the numbers in between A and B, but this time including the endpoints A and B. So all the numbers in between. And then finally, to wrap this up, we'll point out that there's no rule that the two endpoints have to both be less than or greater than, or less than or equal or greater than or equal to. We can have mixed ones. So if I wanted to do, for example, the interval starting at A, ending at B, where I include A, but I do not include B, then when I draw that graph, A gets a solid dot, just like A has a bracket. B gets an open circle because B is not included. And our set is all these numbers starting at A, including A, up to B, but not including B. And then we could do a similar thing, but the other way around, where maybe I start at A, but I don't include it, and I go up to B, and I do include it. So A would have an open circle corresponding to this parentheses. B would have a solid circle, and we would have all the numbers in between them. So you'll see a great variety of inequalities, and frequently the answer to your inequality will come looking in one of these set inequality type forms, and you'll be asked to give one or the other of an interval notation or a graph, or possibly sometimes both. All right, so I would recommend putting this chart somewhere handy in case you get yourself confused. Some people find that this makes perfect sense. I know I had some trouble with which direction was greater than and which direction was less than for a long time. And so I found this chart very helpful in remembering which way greater than pointed and which way less than pointed. So as long as I have it written with the x first and the number second, greater than and less than point the same way as their graph. So that's important to keep in mind. But it only works if I have x written first. If I turn my inequality around, not so much. All right, so just a reminder that open circles and parentheses mean every number up to the endpoint, but not including the endpoint. Closed circles, square brackets mean that we are including the endpoint. So I want to take a couple of examples. Each one of them gives us one form, either set notation, interval notation, or a graph, and we want to fill in the other two. So if I have, for example, the set of x such that x is less than or equal to 5. If I drew that on a number line, less than or equal to negative 5, then here goes my number line. I want to be sure that negative 5 is on here somewhere, and I want to be sure that I have a couple of numbers on both sides of negative 5 so I can tell which way my graph's going. But there's no rule that when I draw my number line like this, there's no rule that 0 has to be in the middle or even on the graph. Use whichever part of the number line is convenient for the problem you're working on. So if I want less than or equal to negative 5, that means we're including negative 5. So I put a solid dot at negative 5, and it's less than or equal, so it's going to the left. If I wanted to write that in interval notation, since it goes forever to the left, I put a negative infinity, and then it stops at negative 5. And since we're including negative 5, it gets a square bracket. It's worth pointing out at this point that anytime you have an infinity, positive or negative, in your interval notation, the end closest to the infinity will always be a parentheses. So since infinity came first here, I start with a parentheses, no matter what's happening on the other endpoint. If I have an infinity, it will have a parentheses. All right, next one. I've got square bracket negative 2 to 7. So if I wanted to draw that on a number line, that means I need to be sure that I have all the numbers from negative 2 to 7. Means I might need to make my number line a little bit longer. Let's see. So here comes my number line. And when I graph it, it needs to start at negative 2 and include negative 2. and it needs to go up to 7 but not include 7. So I want all these numbers in between -2 and 7, including -2 but not including 7. So if I wrote that as an inequality, it would say -2 is the smallest. It gets a less than or equal. X is in between. And then x is less than 7. All right, for the last one, I have a number line. I have a graph. And so I need to give the interval notation and the set notation. If I was going to write an interval notation, I noticed that it has an open circle at 2. So it's going to start with a parentheses and a 2. And it's got an arrow that's going forever to the right, so that's an infinity. And we said that infinity always gets parentheses. So if I was going to write that as a set, it would be the set of all x such that, let's think about what our inequality is. The numbers in this blue part of my graph are all the numbers that are greater than 2. So we're going to write x is greater than 2. Not greater than or equal to, because the dot, the open circle, shows we're not including 2, but strictly greater than 2. It's worth pointing out that that would be the same thing as writing the set of x such that 2 is less than x. So x greater than 2 and 2 is less than x. They mean the same thing, but we generally find it easier to think about it when we write x greater than 2. So I would encourage you, anytime you end up with something like this as your answer, to change it around. Just flip your inequality. Be sure that the big side, when I was in middle school, I think I called this an alligator mouth. And the open side of the alligator mouth always went towards the bigger number. And in this case, x is the bigger number in both cases, and the smaller side goes towards the smaller number. So we want to be sure that that stays the same. Otherwise, we've changed our inequality. But as long as it stays the same, as long as the alligator mouth always opens towards x, no matter which way the alligator is facing, then we've got the same inequality. Let's do a couple more, and that will wrap up our interval notation practice. I have the set of x so that 4 is less than x, which is less than 10. So let's start off by drawing a graph. So there's my number line. These are both less than, so they're both going to be open circles. And we want the part in between. If I was going to write that as an interval, it would start at 4, and because 4 is not included, it gets a parentheses. And it ends at 10, again, parentheses. Negative infinity to 6. That's an interval. If I draw it on a number line, let's see. The negative infinity tells me it's going to go forever to the left, and the 6 tells me that its endpoint is right here. I'm going to use a solid dot because the 6 had a square bracket, so it's included. A negative infinity says it's going forever to the left. So those are all the numbers so that x is smaller than or equal to 6. I know that I need less than or equal to because of the square bracket and the solid dot. All right, one more. I have an interval showing on this graph that starts at 0 and ends at 3, and it includes both of them. So as an interval, that would be square bracket 0 because we're including 0, and a square bracket on 3 because we're including 3. As a set, that would be 0 is the beginning, less than or equal because we're including 0. Put my x in the middle, less than or equal to 3. So there we go. So now we've had a little bit of practice with changing back and forth between inequalities and intervals and graphs. And so that'll wrap up this video on inequalities. And in the next video, that'll wrap up the video on interval notation. And in the next video, we'll start solving some inequalities.